Number 13 then from the 2007 Advanced Higher Maths, parametric equations. A pair of parametric equations, get the derivative of y with respect to x, find the equation of a tangent at a certain point on that curve defined by the parameter at t equals pi upon 8. But first, just a little note on what's actually happening here in terms of these parameters, and a way that you could solve this very quickly, just thinking of the geometry. However, you can't do this in the exam. This is just meant to be an interesting note, so just skip this bit if you like. You use parametric equations whenever you've got curves that fold in themselves. It's the most satisfactory way of being able to identify a point in a curve. A parameter is simply a counting number that locates the position of a point. This one is readily identifiable as the parametric equations of a circle, because if you have a circle centered the origin, then a simple way to locate each point wouldn't be by giving the x and y coordinates, it would just be by giving the angle that you would turn through from the positive x. Because to get the coordinates of that point, you would have this. The x coordinate would be the cosine of the angle, and the y coordinate would be the sine of the angle. And if it just says one of each of those, that must be a circle of radius 1. So interpreting this question in terms of this, it says, as the parameter goes from 0 to pi upon 2, notice these points are moving twice as fast as the parameter because it's double the angle. You're actually going to go from 0 to pi, so that would form a semicircle. Notice it doesn't include the points on the axis. That's deliberate in this question because for the points on the axis, when that parameter would be 0 or pi upon 2, the derivatives would be undefined. You'd have these vertical derivatives here. So what this really says is you've got a semicircle, not including these 2 points, and the question says, what is the equation of the gradient when the parameter is pi upon 8? Well, if the parameter is pi upon 8, 2 times it would be pi upon 4. Pi upon 4, and it's just a 1, radius 1. So that's like saying, what's the equation of the tangent to a circle when the angle is 45 degrees here? Now, since that's at right angles, that means that this then forms a 45 degree triangle. 45, 45, 45. No, it doesn't look like that. If it's at 45 degrees, the gradient must be 1 for the radius. So the gradient of the tangent must be negative 1. If it's 45 degrees, I've got a 45 degree isosceles triangle. Using the ratio of sides for an isosceles triangle of 45 degrees, 1, 1, root 2. The equation of that tangent straight away would be y equals mx plus c. Gradient, negative 1, so y equals negative x. Cutting the y-axis at root 2, so there it is. Just by thinking of the semicircle defined by this, the answer to part A should be y equals negative x plus root 2. Forgetting that then, because this is the way you'd be answering it in the exam, because it specifies this root. It says, what's the derivative of y with respect to x? What's dy by dx? Well, straight away, y is defined here in terms of the parameter t. So the first thing we'd have to do is find dy by dt. Well, dy by dt, the derivative of that would be cos. It's not just the sine of t, it's the sine of 2t. It's acting on a little linear function. So multiply by the derivative of that little linear function 2. So it's 2 cos 2t. The derivative of x with respect to t would be negative sine for the cos part. Again, acting on a linear function 2t. So multiplied by 2. We'll just pop that in there. And then to get dy by dx, I'd have to use this relationship between the derivatives. Dy by dt times dt by dx would produce a dy by dx. So that's going to be dy by dt is cos 2t. dt by dx is this upside down. So either times 1 over negative 2 sine 2t, or you could just write it straight underneath. But the important bit here is I can't get dy by dx straight away because I don't have the constraint equation. I don't have y defined in terms of x. So we'd have to do dy by dt and then find differentials that would knock out the dt and leave me with a dx. So that would be dt by dx. And then that would cancel down to a negative, the 2's will cancel, but it's upside down for a tangent. But that's fair enough because you know the reciprocal of tan is the cot. So negative cot 2t. Divided by dx equals negative cot 2t. Now it said, what happens at t equals pi upon 8? Well, if you want the equation of a tangent, that's the equation of a line. I'll need a point on the line and its gradient. Well, here's the gradient. So a point on the line means finding the x and y coordinates. Well, if t equals pi upon 8, x will equal cos of 2 times pi upon 8. That's pi upon 4, 45 degrees, 1 upon root 2. Y is going to be sine 2 times t pi upon 8. That's sine pi upon 4, 45 degrees, 1 upon root 2. And the gradient, which will be the derivative, will be negative cot 2 times pi upon 8. Now, cot is the reciprocal of tangent. The tangent of pi upon 4 is 1, so the reciprocal of 1 is 1, so it's going to be negative 1. So there's all the features I need to feed into it then. I've got a gradient of negative 1 and a point 1 upon root 2, 1 upon root 2. Now I can get the tangent. It's the equation of a line. I don't happen to know where it cuts the y-axis, so I'll have to use the full equation. Y minus b equals mx minus a. Y minus 1 upon root 2 is negative 1 times x minus 1 upon root 2. So y is going to equal negative x plus 1 upon root 2 plus 1 upon root 2. That's plus 2 upon root 2. And 2 upon root 2 goes back to root 2. You can either think multiply the top and the bottom by root 2, or better than that, within 2 there always resides 2 square roots, and that'll knock out one of them. So that'll give you, for the tangent, I've left myself no room at all, negative x plus root 2. Now the second part says, find an expression for the second derivative of y with respect to x, and then evaluate some expression, which I'll do after. Well, the second derivative of y with respect to x means take your first derivative of y with respect to x and differentiate it with respect to x again. But it doesn't involve x. So that means I can only differentiate it with respect to t. So to get the second derivative, I'd have to differentiate with respect to t, since that's all I've got. And then correct that, or adjust that, with the derivative of t with respect to x, which we already know. Now, the derivative of cot is negative cosec squared. So since I've got the negative already, that will just be cosec squared, 2t, acting on a linear function, multiply by its derivative, so 2 times it. Times, and as before, dt by dx will be the reciprocal of dx by dt. So times 1 over, or simply write it underneath, over negative 2 sine 2t. Cancelling that down, the 2's will disappear, the whole thing will be negative. Cosec is the reciprocal of sine, so I've got another sine underneath, which will give me a cosec on top. So I've got negative cosec cubed 2t for the second derivative of y with respect to x. And of course, if you haven't learnt your derivatives for these various trig ones, you'd have to rewrite cot as not sine over cos, but it's reciprocal. You'd have to write it as cos over sine 2t over 2t, and then use the quotient rule to arrive at that result. You're better making the effort to learn the various derivatives. And then the last part, just show that this expression produces some integer k. Now again, you could continue, if you've learnt them, using the full range of trig ratios, the normal 3 and the reciprocal 3, or you could start reverting back to familiar ground, changing it back to sines and cosines. I think what I'll do first of all is just keep it with the full range that I have. So what have I got? If I've got sine 2t times the second derivative, which is negative cosec cubed 2t, plus the first derivative, which is cot 2t squared, and then see what that comes to. Well, sine would be written as a cosec underneath, if you like, or you can think of that as being the sign underneath. Whichever way around, that will knock out one of those, leaving me just negative cosec squared 2t. That will now become positive, plus cot squared 2t. Now at this point, there is a connection between these. You don't need to learn all of them, but you certainly should remember the first one. I'll just abbreviate it here. Sine squared plus cos squared equals 1. Gives a connection between sines and cosines. From that, you can derive two other identities. One involving sec, one involving cosec, just depending whichever one you want. Well, here I've got cosecs and cot. This identity can produce connections between sec and tan if I divide them by cos's to get secs. So that would then give me a tan squared plus a 1 equals a sec squared. If I happen to have an equation that had secs and tans in it that required changing into each other. Or, again, sine squared plus cos squared equals 1. If I want cosecs and cots, then I can divide everything by sine squares to get cosecs. So over sine squared, over sine squared, over sine squared. It's going to give me 1 plus cos squared over sine squared would be cot squared equals 1 over sine squared, which is cosec squared. And that's the connection I've got here. So if I knew that identity, I can go straight from this to the answer without having to change back to sines and cosines. So at this point here, when I arrived at this, I would think, right, there's a connection between the two of these, and you could quickly take a note of it somewhere just out of sight. Sine squared plus cos squared equals 1, and then think of divide all by sine squareds, and then you could write down here, you could say, well, since, and you've got 1 plus cot 2t equals cosec squared 2t, then cot squared 2t would be cosec squared 2t minus 1. So I could replace that in here. So I've got negative cosec squared 2t. I mean, it is actually quite obvious that if you've got cot minus cosec, cot take away the cosec, the answer is going to be negative 1. But there's meant to be 5 marks in this altogether. So I'll just plod through this bit. Then the cot can be replaced with plus cosec squared 2t minus 1, which obviously then comes to minus 1 in that form. And it said state the value of k. Well, that means k is negative 1. Or, if you didn't feel brave enough to venture into those reciprocal lands, you could always turn this back into the familiar sines and cosines. So that you would have instead, that's a sine 2t, nice and friendly. Cosec, that's 1 over sine. So negative means times negative 1 over, but that's cubed, over sine cubed 2t, plus that negative being squared will disappear. Now cot is the reciprocal of tan, so instead of sine over cos, it's cos over sine, but it's squared, so it's cos squared 2t over sine squared 2t. Then realising that that sine will cancel out one of these underneath, they're both over sine squared 2t. So over sine squared 2t, I've got a negative 1 plus a cos squared 2t. I'm still going to have to use one of those identities. I'm still going to have to use the fact that sine squared plus cos squared equals 1 to resolve the top of this, so that I can replace cos squared with 1 minus sine squared. So I'll say cos squared 2t is 1 minus sine squared 2t. So I've got negative 1 plus 1 minus sine squared 2t over sine squared 2t. That cancels down to negative sine squared, I'll write it down anyway, negative sine squared 2t over sine squared 2t, which equals negative 1, obviously, because it must give the same answer. And then the same as before, so k equals negative 1.